The broadcast is now starting. All attendees are in listen-only mode.
Good afternoon, ladies and gentlemen. Welcome to TechGeek webinar series, our endeavor to empower techies. We believe that sharing of knowledge is key to enhance our skills and grow us as a professionals. With this principle in mind, we have initiated a series of webinars conducted by various industry experts to give you all a crisp insight of various domains. The topic of today's session is Hadoop MapReduce, and our guest speaker for today's webinar is Mr. Raghavan. He is lead architect Big Data at OSSCube. Raghavan has broad and deep experience across technology, process and management at OSSCube. He has over 17 years of experience in IT industry and has delivered critical and strategic IT solutions to clients in multiple industries with deeper experience in insurance and finance industry. In the past, Raghavan has worked with Indegene Life System, Wipro Technologies and Halasoft Technologies, with major focus on enterprise architecture, integration, web-based solution, databases, BIDW, and big data technologies. Some of his recent roles include independent consultant, associate director technology manager, where he delivered high-performance application for Zurich Insurance Company, Mars and McLennan, Pharma Insurance, Novartis, etc. Data has been his major interest, and he has a very strong background in databases, data modeling, and data warehousing. In the last few years, he has added big data technologies to his portfolio. He is also a Cloudera certified trainer for developer and administrator classes and has conducted several training and consulting assignments. In the Hadoop stack, his experience cover Hive, Pig, Flume, Scoop, administration, HBase. He is also familiar with NoSQL technologies such as MongoDB. He is currently pursuing further learning in machine learning and data science. Raghavan holds a BTech degree in electronics and communication from NIT Warangal, India. So before introducing you all to our guest speaker, we have today Mr. Anurag with us. He is also associated with OSSCube and will brief us about OSSCube. So over to Mr. Anurag.
Hi, thanks everybody for taking time out of your busy schedule for this webinar on MapReduce. I am Anurag Dutt and I'm Senior Business Development Manager for OSSCube, and I will briefly give you a small introduction on the OSSCube. OSSCube is a global solution provider. We deliver integrated mission-critical solutions using open source. We have offices across US, UK, and India, and we have offices across US, UK, and India, and we work with customers across more than 16 countries to deliver robust, scalable, and high-performance solutions using open source technologies. We have the world's largest pool of certified Lamb developers with us. We are the world only Zen Center of Excellence, and we basically work on open source technologies to create the business solutions for various enterprises. This slide showcases basically that OSSCube has a broad set of competencies, but our greatest strength and what separates us from other open source solution providers is our ability to integrate many applications into solutions that can help meet customers' business objectives and differentiate customer from the competition. We have competencies across Sugar CRM, Zench, Process Maker, Talent, Cloudera, Drupal, Magento. And we basically work with all these solutions and products to develop a solution for the enterprises. This is a slide on our big data partners. In partnership we offer extensive big data capabilities to the customers. We are the gold partners for talent, and we are the only talent partner in Asia Pacific and India, and we also cover multiple geographies in UK and US. We are partnered with Microsoft, the leading open source workflow process automation tool. We are the preferred partner with the cloud era for the global corporations who are looking for solutions in big data management and big data analytics for the data-driven applications. We help organizations leverage the power of Apache Hadoop technology and cloud era big data platforms to drive business value from data within and outside the organization using our full line of cloud era and Hadoop consulting, integration, and training services. We are also the
We can hear you, Anurag. Please go ahead. Anurag, we can hear you. Please go ahead. Anurag, are you there? So I think Anurag has just got offline. So I will just move to our presenter, another presenter. He is Mr. Raghavan. Over to you, Raghavan.
Yeah. Yeah. Hello, everyone. Good afternoon. First of all, I would like to thank all of you for taking the time out for this webinar today. Myself, I'm Raghavan Soliam. I'm a lead architect at OSSCube in the big data portfolio. And I do a lot of blogging on big data technologies and webinars. So I love to do this and love to work with open sources, and that's the reason why I'm associated with the OSSCube. I'm today very excited to present this webinar. We have over 100 people in this webinar. It's so exciting to see all like-minded people coming together and trying to share a topic, learn something new. And what made this possible, bringing all of us together here, is the technology. So I'm not just talking about the webinar or the internet or the statistics or whatever is making our conference possible, but actually bringing us together through data, right? So these services or the people who are trying to organize a conference or trying to sell their product, they gather the data from various sources and try to figure out who are like-minded, the people who would like to purchase this product, who would like to attend this conference, who will be interested in this webinar. So these kind of analytics are done, and it is very common nowadays. Every enterprise is doing the analytics by sourcing data from various medias today. It could be Facebook, Twitter, or a generic website, or from various sources, right? So this nowadays we can see the startups, we can see smaller enterprises doing this data-oriented analytics, data-oriented products, data-oriented business. And what made this possible is on the top it comes MapReduce. So MapReduce has made it possible to analyze huge amounts of the data in an economical way so that enterprises can thrive. Enterprises can make use of huge amounts of data which was just left on archives sometime back. So we will see what MapReduce is, how this has made this data processing of huge voluminous data possible. So today, these are the objectives that I want to achieve with all of you. So understand what MapReduce is, and then understand the workings of the MapReduce, how internally it works. And then what are the limitations of the MapReduce? Can it do everything, or are there something that it cannot do? And then the new architectures which are beyond MapReduce. the architectures which support something that cannot be done with the MapReduce. And the alternates to Hadoop MapReduce. Right? So these are the things I want to achieve towards end of this webinar and motivate you to go and learn more about big data technologies or Hadoop or any tool that is of your interest. So the expected audience, it could be anyone who is enthusiastic about the big data technologies or Hadoop in specific. They could be architects, technical leads, senior developers, QA professionals from data warehousing or any other technological platforms that we have today. So first of all, what is MapReduce? It is simply a technique to process distributed data. You have distributed data, you can go and process this data using the MapReduce, right? And it is published by the Google. This technique or the paradigm or the procedure was published by Google during 2004. How a distributed data set can be processed. So why, first of all, distribute the data? When you have the data, why distribute? The answer is, it is big data, right? We have been hearing about this big data, so many times for such a long time. Nowadays, everybody talks about the big data, right? So because it's big data, we have to distribute it. We will end up distributing it because it's huge, and it's also not possible to store it on a single machine or a restricted group of machines. You can have a number of machines tied together, and probably you can store your data. But the problem there is the scalability. One is you cannot store all of this data on a single machine. Second is if you have restricted machines, a set of machines, you cannot scale it at will. So, but is that the only way to process the data? MapReduce is the only way? The answer is no. The big data had been there for a long time. So only recently we named it as big data, and we have been talking about Hadoop and distributed file systems and MapReduce way of processing. But the big data problem had been there from a long time, right? So there are so many other architectures for processing these kind of volumes. In the earlier days, or even today, we have some of the systems running in this way, where we store data on a central repository, and then we have various servers accessing data from the central repository and processing on their machines, processing on each individual machine. But the problem with this is it cannot scale. The reason is, if you have 1,000 such machines, here I have 4 machines in this schema, which is called as a star schema. If I have 1,000 machines, all 1,000 machines will simultaneously try to get data from the central storage, which means this central storage will suffer at a certain number of machines. It can support only a certain number of machines, beyond which it will suffer. And beyond that, even the bandwidth, you have to have so much bandwidth to send this data across to the processing nodes. So it is not scalable, right? And then you have to have very costly servers on the processing nodes or on the storage side. You have to have very costly servers. So the cost is a major factor, and the performance, as I said, beyond a certain number of nodes, the bandwidth it will suffer due to the bandwidth, and it will suffer due to the cost of adding furthermore machines, right? So this is not really scalable in terms of performance and in terms of the scales of economy, right? So how MapReduce is different, how it can alleviate this situation that is posed by the other architectures that we have seen, the star architecture, the star schema that we have seen on the previous slide. And there are various other architectures similarly to process, to hold big data and process it. So how MapReduce is different from these architectures? So one is, it will let you process the data on a distributed file system. So first of all, as I said in the first slide, it is a technique to process distributed data. So you have to have ability to distribute the data, which is nothing but a distributed file system. So the MapReduce will let you process the data on a distributed file system, and it allows you to process data discretely on the individual servers, which means you have a big file. So let us take a look at the illustration here. You have a big file, and this file you should be able to distribute on a cluster of machines. So they could be cheap commodity servers. So when I say cheap commodity servers, I am not talking about the second-hand laptops or second-hand desktops, but the servers. They should be server-grade machines, which are cheaper than your special server hardware. So you have this cluster of servers where you have distributed your file. So what's happening here is this file is being split into smaller chunks. The whole thing is not copied, but it is split into smaller chunks and copied on all these various machines. And the MapReduce, what it can do is it can execute the user program on all of these machines. See, this is where the wonder is happening. You have a big file of let's say 10 GB or 100 GB. You have split that into 1 GB each on all these 100 machines. And then your program is going and executing on or processing each of this 1 GB chunk. So your processing is 100 times faster, right? But the challenge here in this kind of processing is that you want to get some metrics, you want to get some analytics of the entire data, not for a single piece of data. But here in this way of processing, what happens is on each of the server, you are ending up with a partial result than a full result. So how do you combine this result together to say that this is my whole numbers or whole metrics or whole statistics? So the MapReduce can do this. MapReduce can gracefully combine all these partial results on all these discrete machines and present you a integrated view of all the processes, all the processing done on the individual servers. So it can process the data on a distributed file or distributed data, and then it can gracefully combine this data. So these are the main abilities of the MapReduce. And also the way, and all of this process we are not doing as developers or the system builders. The MapReduce will have these abilities. The MapReduce, the engine that you are building or a particular vendor is building should build in all these capabilities. They should be able to launch the customer program on all the different pieces of the data, and then they should be able to bring in all the partial results and be able to combine and give back the combined integrated result. So these are the abilities that MapReduce should bring in. So this is what exactly Hadoop did. Hadoop has two core components. One is for the distributed file system, which is called as HDFS, which can take your data, a huge file, and split that into smaller chunks and store it on various machines in the cluster. And the MapReduce part of the Hadoop or MapReduce framework or MapReduce engine, different people call it as with a different name. So this MapReduce can execute user programs on the cluster where data is there. So the wonder here is that the program is going to the data. You are not bringing the data to the program like we have seen in the previous Tor architecture, which means you are saving enormous bandwidth. Your program is very minuscule compared to your data. So it does not take much time to actually travel to the server where data is sitting. So you're completely avoiding the data movements. It's not really complete to the maximum extent, maybe 90–95%. You're not moving the data, but the program is going to the data chunk and runs there. And the partial result that is produced on that server will be combined back by the MapReduce engine. We'll shortly take a look at how exactly this, the whole process happens. But if you take the main prominent open source implementation of the MapReduce, it is the Hadoop. So Hadoop has a MapReduce implementation, and to support MapReduce, it has a distributed file system called as the HDFS. And I also have Yarn here. We'll also briefly talk about Yarn, what it is, and what is the connection of Yarn with the MapReduce also we'll see briefly. Right. So now we will see the internals of the MapReduce, how exactly it can process and combine all the partial results across a huge number of clusters. So as I just described, to process data on the Hadoop, you need a distributed file system. The distributed file system, if you take the case of Hadoop, it is HDFS. So HDFS, if you give a file to the HDFS, it can take it, it can split into smaller chunks and place it on various machines based on the number of machines it has, or based on number of splits it has created out of the input data. So once you have this, right, when you install Hadoop, typically you will have HDFS as well as MapReduce both, though these two are two different systems. One is a distributed file system, HDFS, and the other one is the MapReduce, which can process the data that is sitting on the HDFS. So now, taking this as the precondition that we have HDFS ready and we have put a file on the HDFS, and this has been split into n splits, 1, 2, 3, up to n. So now how MapReduce can process this data? Right? So you have a MapReduce engine that comes along with the Hadoop. So now the user can write MapReduce programs using the interface, programming interface of the MapReduce. Typically it is a Java. You have a Java API, you can write the MapReduce programs. The MapReduce program typically consists of two components, two major components. One is the map component, other one is the reduce component. So far, I have given a picture of the holistic program, or the whole program together working and giving you the result, working hand in hand with the MapReduce engine. But actually, the MapReduce program consists of two major components, a map and a reduce. So this is what, these two divided components is what gives the ability to combine the partial result. So we'll see how it happens. So when you develop a MapReduce program and execute it on the Hadoop cluster, what happens is the map program that you have given, this is a single program, so don't think that these are multiple programs. It's a single program. It has been deployed onto each server to run the process on the individual split. So your map program, out of your map and reduce component, your map program runs on each individual server on the individual split of the file. So now you have the partial result that is given out by the map program, the map component of your job, your Hadoop MapReduce job. So now what reduce program that we just spoke about can do is that it can receive the partial result from each of the map so that it will combine the result on the reduce side. But how do they get the data? How do reduce get the data from the maps? So that is where the MapReduce framework comes into picture, and the MapReduce framework will execute an intermediate phase called as shuffle phase. So what shuffle phase can do is that it will identify the keys, identify the relevant data in the intermediate result produced by map, and it will divide that by the number of reducers. So here also it is achieving parallelism. If you see on the map side, it is doing the parallel processing, and even on the reduce side, it can achieve the parallelizing, thereby increasing the performance, increasing the speed of your job. So it will smartly divide the intermediate result between number of reducers. So you have, let's say, 30 keys. It is possible that 10 keys will come to one first reducer, second 10 will come to the second, third 10 will come to third. Thereby, you are increasing even the reduce phase speed by 3 times, right? So on the other maps as well, the shuffle phase will take care that the same key on every mapper will reach the same reducer. Let's say you have a key apple here, okay? The MapReduce engine's shuffle phase will will guarantee that the apple from this map, the apple key from this map, this map, this map will reach a single reducer. So we were talking about the split result or the partial result scattered across the cluster on various machines where the maps have run. Now, by the shuffle phase, we have guaranteed, or the MapReduce framework has guaranteed that the similar keys will reach the same reducer. Now it is as simple as applying your the metric. It could be addition, it could be average, or it could be you may want to apply a very complex statistical function on that particular key and the corresponding values. So the MapReduce shuffle phase is what makes this possible. That executing on the various machines parallelly and then be able to get an integrated result. So this is what goes on in the background of the MapReduce execution. A map phase, which will go to a shuffle phase and then reduce phase. And once the reduce phase or the reducers on which on the machines where these are running will write the data out. Either it could be to the distributed file system, or it could be to any other file system of your preference. It could work with S3, it will work with various other file systems as well. It's not restricted to the HDFS. Right? So this is the brief working of the MapReduce, how exactly it works. Right? So, but how this is made possible? So I'm talking about MapReduce framework, shuffle phase, and then someone launching this your map task or reduce task without your interference. You are just giving the map program and the reduce program to the MapReduce engine, right? And then it is taking care of all these things. You are free of all these burdens, shuffling and where which program is running, where your file splits are sitting. You don't need to bother about all those things. But how is this made? It is made through the MapReduce, the framework of the Hadoop. It has the processes, it has the daemons running. When you say your MapReduce is running, you will have all these pieces running on various machines which will coordinate, which will take your job, which will launch the maps, reducers, right? If you see the MapReduce of the Hadoop, you have the job tracker, which is the central controller of the job execution or the job control. And on individual machines, I'm talking about a cluster of machines, 100, 200, right? It could be any size. So on these machines, you will have another process or daemon running called as task tracker, which will take the instructions from the job tracker to run a specific map on a specific file split, or run a reduce on a specific key and its set of values, right? So this, so here I am representing the map and reduce together. Does not mean that they will run together. These are the slots. These are the capacity of that particular node, of that particular task tracker, how much work it can do, how many tasks it can run, right? So all this framework, the job tracker, the task tracker, and all the the shuffle code that the Hadoop MapReduce framework has, is making this MapReduce program execution a possibility. Right? It's a very complex system to execute parallelly, monitor it, and then make sure that any failures are recovered. It's a highly fault tolerant system. The Hadoop MapReduce is a very highly fault tolerant system that even if a particular task fails, it has the ability to restart. It has the ability to recover from that specific failure without restarting the entire job. So that is the Hadoop MapReduce, the architecture. What exactly the daemons that it has and how they make it possible to execute a job on the cluster, MapReduce cluster. So here, though I have represented the HDFS as a separate, a single box, It is not a single thing. I just represented that as a system, HDFS system. HDFS system is also very similar to what we are seeing here on the MapReduce. It also has a master and slave demands. But for the simplicity's sake, I represented HDFS as a single system, which is accessed by your jobs. It could be job tracker or the task tracker for getting the file system information. So, but will it survive the data deluge? Why this question is coming in the first place? Because the demands are changing, right? So if you see the MapReduce very closely, it is a batch-oriented system. When you run your job, it has to initiate the map task on each individual machines. It has to find out which machines are available. It has to monitor. It has to do the shuffling. It has to aggregate, run your reducers. So it has some lead time. It has some initiation time, setup time, and then you have so much of data that you are processing, right? So it is mainly meant for the batch processing. It is not like your RDBMS, right? You just say select something from somewhere, it will immediately show you. It is not the real-time responsive system. It is a batch-oriented system. That's one of the limitations or shortfalls of the MapReduce system. And also, not all problems can be solved through MapReduce, right? There are certain use cases, certain problems in the industry. Typically, the graph problems where you have to traverse the entire graph end to end. And some of the scientific problems where you need to have all the data together to process. The MapReduce is taking the advantage of the distributed system. Data is split across, scattered, and then it is going and individually handling each piece. But not all algorithms can work like this. Some of the algorithms will need all of the data together then and there to process and get the output. So some of the problems cannot be solved through the MapReduce. And we are also getting very impatient, right? We want to get everything on our mobile, and enterprises want to know if anything has gone wrong with their systems or anything gone wrong with their products or their reputation. They want to know instantly, right? Somebody posts some bad tweet on their product on Twitter. They want to know within 4 or 5 minutes. So I'm outside. I want to get the message on my mobile, so that I can take a corrective action. These are the kind of demands that are coming today. And again, so though in the beginning I said the data volumes as one of the challenge, that is not the only challenge actually. The challenge is also about the responsiveness. The challenge is also about the structure of the data. The data that you are getting from Twitter, Facebook, or any media or website of your interest will not be structured. You can make some sense out of it. You can attach some structure to that, but it will not be in a structure that you want, where you can comfortably load into your database or your data warehouse and process it. Each website will have its own format. Each the person where you have the data publicly available, they'll have their own structures. So that is also one challenge. You want to process all kinds of data. They are all voluminous, and you want to, some of the times you want to process them instantaneously. Immediate gratification we want. So these kind of things again cannot be addressed by the MapReduce by its batch processing nature. So what's going to happen to MapReduce? Is it going away? Is it going to disappear? My sincere answer is no. It is not going to disappear, because you want to process the distributed data and get an integrated result. You need some way to combine it at one point of time. They need to crisscross, they need to touch each other and group together with the similar kind of data in one place, so that you can say there are 10 apples 100 oranges, so on and so forth. Otherwise, you cannot. Otherwise, you have to move away from the distributed file system or distributed system, which means that you are getting back to the older architectures which suffered with a lot of bottlenecks. So my belief is that the MapReduce is not going to disappear, but it is going to improve. It is going to adopt itself to turn into different forms, different shapes, right? So we already see some of them, and also when the experts or when the people talk about no, MapReduce is not going to exist, it's going to disappear. So what most of the times they mean is the Hadoop MapReduce, or maybe the Hadoop MapReduce API or the specific implementation, because there are some pitfalls in the way the Hadoop MapReduce is implemented. It processes one key at a time, right? And then it cannot store the state while processing. There are some certain things which there are workarounds, but it will be cumbersome. So I believe the Hadoop, the MapReduce implementation might change, or some alternates or some variations of that MapReduce will be adopted, will be created by different products or different tools that are coming on top of the Hadoop, which will still will use MapReduce, I believe. So we'll see that shortly. Right. So what are the alternates to the Hadoop, the MapReduce? So one of the alternate, I don't call it as alternate, the yarn. Yarn is actually, it tries to improve the MapReduce. It tries to improvise the MapReduce. At the same time, it will allow other kinds of applications other than the MapReduce to function. So what is a MapReduce application? MapReduce application consists of a MapReduce along with the shuffle phase introduced by the MapReduce engine, and then it will give out the analytics that you are desiring. So that is a MapReduce application. It is not an integral part of the Hadoop or any other system. So the pitfalls or the shortfalls of the MapReduce are covered by yarn, and yarn actually grown as a separate the application which can host a MapReduce application and various other applications as well. So yarn, what is yarn? It is yet another resource negotiator, and also some of the people say that it is also Yahoo resource negotiator because it's basically took birth in Yahoo's team. But it's popularly called as yet another resource negotiator. So which actually relieves the MapReduce of the responsibilities of launching the job, scheduling the job. So all these kind of things, so generic resource management. It will relieve the MapReduce from all these things and just let it do its job execution and job monitoring, these kind of things. But whereas the cluster resources such as allocating the resources on each of the machine, so these kind of things are handled by the yarn framework. So now the MapReduce becomes a simple application that runs on top of yarn, and this MapReduce is actually called as MapReduce 2. The previous one is named as MapReduce 1, and the MapReduce that runs on yarn is the MapReduce 2. So what this gives, yarn gives, is enormous scalability, because it is not monitoring the individual jobs anymore. It is just taking care of the clusters resources such as the machines, the RAM, and then the availability of these machines. All these kind of things are taken care by yarn, whereas the individual jobs, individual applications such as MapReduce, and some other applications that have taken birth on Yarn or that have been migrated to Yarn later on, which we will shortly see. So those applications individually will take care of their applications, recovering from failures, and then monitoring and then collecting statistics from their job when it is running. So all these kind of things are done by the individual applications like MapReduce, or it could be applications like Impala, it could be HBase, any other application that can run on Yarn. So the Yarn not only improved the MapReduce one, but it also has given the possibility, opened up for so many other applications which can run on Hadoop today. But the question is why those applications should run on Hadoop. The reason is the Hadoop is not only a processing engine, but it is also a data store. It has all the data that you want to process, your big data, on its HDFS platform. If you want to process the data, earlier it used to be the only MapReduce way of processing, but now you can process this data in several other ways, right? So what are the other ways of processing data on Yarn, or processing the data on which is residing on HDFS? So I just wanted to show how Yarn is different from the MapReduce. In MapReduce we had job tracker here, so this has been replaced by the resource manager, which takes care of only the resources, scheduling, and then allocation, and then monitoring of the individual nodes. That's all what it does. But whereas the individual job management will be done by the individual the application frameworks. Earlier, also one of the key difference between the MapReduce one and then this Yarn architecture is that we had the map and reduce slots in the previous architecture, but if you see here, we have something called as container. These are called as containers, which are generic processing units or processing capacities, right? Where not only map and reduce, but any kind of task can be run. If you design your own Yarn application which can run on Yarn, and you want to run a different kind of process, it could be shell script, it could be a Scala program, it could be a Python program, a C program, it could be anything. Now it can be run on this container, which is the capacity for processing. It could be capacity in the sense a finite amount of RAM and then finite amount of the CPU cores. Right? Now the possibilities have opened up. So what happened further is that a lot of applications have migrated to the Yarn. Thereby, they also can relieve themselves of the resource management, the cluster management. They can focus on their core functionality. So some of these applications that have come on Hadoop alternative to the MapReduce or Impala. There is another application by name Spark, HBase. HBase was there, but HBase is later migrated to Yarn, and then Giraffe. So Impala, it supports SQL queries. You can write SQL queries to access the data on the HDFS with a little bit support of the metadata. You can write queries in the MapReduce and then get your data out. Spark, on the other hand, it is a very powerful. We'll briefly speak about Spark as well. It's a very powerful and promising replacement for the current Hadoop MapReduce, and then it can work on different workloads, not only the batch or online. It can support different workloads. And then we also have HBase. HBase is called as the Hadoop database, which comes under the NoSQL database the category. Giraffe is another application that has come that has been migrated to the Yarn platform, which enables you to process graph-oriented processing. you have graph data, you'll be able to find shortest path or various other graph algorithms you'll be able to execute on the Hadoop using the Apache Giraffe. So what is Impala, right? Impala is an alternate to the MapReduce way of processing the data. So Impala has its own the framework. It does not depend on the task tracker or the job tracker that we have shown on the MapReduce 1 architecture, but it makes use of Yarn for resource management, resource allocation. But it has its own daemons running on each of the machine on the cluster. It is aware of the data formats, that when you write a SQL, it understands what exactly you want. It maps to the layout of the underlying data in the HDFS and processes the data and then gives you back quickly. So what Impala achieves is that it is actually cutting down the launching time. If you see a MapReduce job, it takes a lot of time to launch, find out the resources and then launch your maps and reduces, all those things. Because the Impala daemons are always running, it cuts down on the startup time. It achieves a great performance jump due to this. But internally, Impala also uses the MapReduce. MapReduce processing, it is not Hadoop MapReduce, but it uses the MapReduce jobs. A smaller MapReduce, its own MapReduce jobs, it will use internally to process the data. And it also uses the caching. It can cache the data so that further queries, if you are using a particular data set multiple times again and again, the frequently used data sets will be cached. Thereby, your query response will improve dramatically. So if you are looking at a SQL engine on the Hadoop with a reasonably real-time response, I've seen some of the queries that runs on the Hadoop, which takes around say 1 minute. Impala has given out in a matter of a few seconds. Right? So that's the kind of performance improvement that they have brought in by delinking with the Hadoop, the MapReduce. So if you're looking for a SQL engine on top of the Hadoop, Impala, you can consider Impala as one of the fitting options. And then Spark. Spark is again an Apache project, which is a sub-project of the Hadoop now. So it also has its own framework like Impala. It has its own daemons running on individual servers. It also has a master which will coordinate all these jobs. But this can run on top of Hadoop Yarn. It can run on Yarn so that Spark again is freed up of its responsibility to take care of the cluster resources. It can just focus on its processing, its jobs. It does not depend on Hadoop MapReduce. It also can process MapReduce kind of jobs. But the the best part about the Spark is that it can process different workloads. Unlike Impala or unlike Hadoop MapReduce, it can process different workloads. It can process a batch-oriented jobs, which is a MapReduce oriented. It can process data streams that is just coming through tools like Flume or any other data streams. It can take that and it can process this data in real time. Of course, it runs on Yarn. It also uses cache very efficiently to do in-memory processing. So this is supposed to be the future of data processing on the Hadoop because it has the multiple options: batch processing, real-time querying, stream processing, all kind of things that typically we talk today in the big data domain. Spark can do. Right. So very soon, I think you can see the jobs being written in the Spark, jobs being migrated to the Spark. One of the best thing about Spark is that you can write your programs, unlike in traditional MapReduce where you write in Java. You can write your programs in Scala and Python. So these are high-level languages, very beautiful languages for processing your data, very expressive. You don't need to do very minute operations. You can operate on your data at a very high level in terms of transformations, in terms of filtering. It's very easy to learn and write as well. So I think that the adaptability of Spark is very high, and then I think it might replace some of the prominent components of the Hadoop that we have today. I mean, permanent in the sense it will not replace, in the sense it will not kill it away, but it will bring in some transformation, I believe. Right. So this actually brings us to end of this presentation. So now we have some time for the question and answers. So I'll open it up to questions.
Thanks, Raghavan, for such an insightful presentation. Let us quickly move to the question and answer round. I request you to please read out the question before answering them, so that all our listeners get the commendable insight. So quickly take up the question. Please take up the first question, Raghavan.
Yeah.
Are you able to see the question, Raghavan?
Okay, fine. I'm just opening it. I think I was in a wrong window. Just my window is not expanding. 1 minute. Just 1 minute.
You have to go to the question section. You will find question there.
Yeah. So it is actually I'm not able to expand it.
Please double click on it.
Okay, so yeah, one of the question is what is a task instance in the Hadoop and where does it run? So the task is nothing but, if you see the MapReduce job that we have seen, it has two main parts, the map and reduce. So any of this can be called as a task. A map can be called as a map task, reduce can be called as a reduce task. So where does it run? It runs on any of the cluster machine, in the cluster. Like we have seen, a map task can have multiple instances depending on the number of data splits that you have. So it typically runs on a machine where the data is present. Right? So that's the answer for the map task. But where does reduce run? Reduce does not have this kind of a restriction, that data locality. The data has to come across the network, which means it can run anywhere on the machine. So the answer, just to summarize, a map task typically runs on a machine where the data chunk is present, but whereas the reduce reduce task can run anywhere. Okay, so I'll take the next question. Okay, does MapReduce work on AIX? Yes, it should run. AIX is a different flavor of Unix. So this Hadoop runs on Unix comfortably. So you can deploy on any of the Unix flavors, and then it should be able to run. So that's not an issue. So one of the question is, can you explain me the role of application manager and application master in Yarn? So this actually goes a little bit into the Yarn architecture. The application manager is nothing but is a component of Yarn which actually takes communication, which actually communicates with application masters, which are taking care of the individual applications. But whereas application master, so this naming is a little confusing, right? But these two have two different responsibilities. But whereas if you see application master is nothing but a process which is monitoring a specific job. An application master will be one application master per job. But whereas application manager is a part of the Yarn framework, which takes care of communication responsibility with the individual application managers, application masters, which are running per job. Okay, so another question, I think it's not very clear concerning the data security, encryption, and the system security. What kind of security systems Hadoop framework has? Yeah, this is a very interesting question. The Hadoop, a plain vanilla Hadoop does not come with any security at all. It just comes with authorization for good people, but not for the bad people wanting to do malicious things. So it has authorization at the file system level, HDFS file system level. But the recent versions that are coming for the past 2-3 years support authentication as well. Authentication, if you integrate that with the Kerberos authentication mechanism, where the individual user is verified and authenticated and then be allowed to perform many operations on the cluster. But it's very complex. Typically, they don't go for this kind of secure clusters. But yeah, you have an option to integrate with Kerberos. Encryption wise, HDFS do not support encryption at this point. But using Kerberos, you can use SSL for at least encrypting the data that is being sent on wire. But HDFS does not support encryption at this point. But intermediate data that we talked about, that can be encrypted. So that can be compressed. Compression is different from encryption. So encryption is not supported in Hadoop at this point. What is custom partitioning in MapReduce? Okay, so this is like going a little bit into the internals of the MapReduce. So custom partitioning is basically, we have seen on the MapReduce processing slide that the data, intermediate data from the maps will reach out to Reduce, right? So there should be some criteria which determines which value or which record should go to which reducer, right? Which will, and also that should ensure that the same kind of key on all of the intermediate data sets should reach one and only one reducer. Otherwise, you will end up with some kind of split brain syndrome, right? This process is called as partitioning, right? This can be controlled. There is a default partitioning, like how you want to partition. If you want to control, you can go for a custom partitioning, which you have to write some Java code. So that is what the custom partitioning is. So the next question, do we have cloud solutions for big data centers across? Yes, definitely. So there are a lot of cloud providers like Rackspace, Amazon Web Services. They support the cloud-based solutions. In fact, Amazon has just a server kind of setup, like which comes in EC2, where you can set up your own the Hadoop, or it comes with a pre-configured Hadoop as well. You can do that. And in fact, Hadoop has some APIs built, which is one of them is EC2 API that comes with the Hadoop. The exact name could be slightly different, but there is an API using which you actually can operate on the Amazon cluster, Amazon Hadoop cluster that you just launched from your desktop, from your console. You can do that. And Amazon also has something it's called as EMR, Elastic MapReduce, where you don't need to set up, and on demand you can launch a cluster with any number of nodes. Just run your data, process your data either sitting on the S3 or on a different kind of file. S3 typically is supported by EMR. You can process the data from S3 and then it automatically, you have an option to automatically terminate the cluster when your job is completed. So it is like, just pay a, per view kind of model. You just use it, and for the time you just pay, some money to Amazon. So yes, there's plenty of cloud support by Rackspace, by Amazon. There could be a lot of other providers as well. IBM has, Microsoft has support for Hadoop on cloud. So next question, as you told about Giraffe, it is used for graph processing. Could you please explain in brief? See, it is, it will take, I will not be able to do justice in just 5 minutes. So it's basically graph data is, it will have a connected data. Connected data, typically it is for maps, or it is for social networks. These kind of things. So using this data, you'll be able to traverse and find out what are your nearest things, what are your nearest neighbors, what could be your possible interested neighbors, something like not only from social media, but also from the roads and the maps, electrical networks, a lot of things the graph applications is applied. But exact working of Giraffe, this we will not be able to get in. The next question, how does the Scala fits into big data framework? So like I said, Scala, okay, your question is about Scala. So Scala is a language, right? And Spark uses Scala for writing its data processing steps. Right? You can create a data set, load a data set. Let's say your data set is, let's say DS. A variable that I created on in my Scala program. You can say ds dot filter by, ds dot transform. So there are the certain language features where you can use them to transform into different formats. So it's just a language which Spark has chosen to use, and in fact Spark itself is developed in Scala. Yarn, it runs on top of Yarn because Yarn will support a generic program rather than a Java program in a container. So your Scala program will go and run in Yarn container on the individual nodes. So that's how the Scala comes into the Hadoop world. So this is probably the last question I will take. Can I install Apache MapReduce, a vanilla version on Windows? No, you cannot. You cannot install vanilla version because the way the Apache MapReduce, Apache Hadoop is built, it follows a lot of Unix syntax, especially while accessing the files. It has some Unix shell scripts as well internally. So it cannot directly run on the Windows because of that reason. But as a Java application, it should run anywhere. But Apache will not run. So Hortonworks, along with the Microsoft, has put effort to migrate that to Windows. So Hortonworks has a release of Hadoop, which actually runs on the Microsoft Windows directly. So maybe you can try out that version. So just a minute, let me see if any more questions. I'll take one more question. Okay, so what is a map file and a Bloom map file? So these are certain data structures. Map file is nothing but you have the key value combinations put in a file structure, right? So there's also another file called as a sequence file. So whereas a Bloom map is a algorithm, there's a algorithm called as a Bloom filter, which is used for representing huge amounts of the data so that it can be used for filtering. right? So the file generated by this process is called as a Bloom map file. So there's a lot, a big algorithm behind the the Bloom map. So there is in this book you get a very beautiful explanation of the Bloom filter, which is called as Hadoop in Action by Chuck Lamb. So you can refer to that book. Map file is a very simple structure where you have the key and value combinations sitting in a file for Hadoop. So okay, I think that is I think that also brings us to the end of our questions. So once again, I would like to thank all of you for taking time out. Hope you had enjoyed this session and got some understanding, and you are encouraged to pursue further on this domain.
Thanks, Raghavan, for taking so many questions. Still, this is very hot topic, and we are getting lot of questions from our participants. So once we are done with the session, we will share all these questions to you. If you please take out some time to answering these questions on our TechGeek website. So I am really thankful to our guest speaker for conducting this webinar. It was indeed a great session. I would also like to thank all our participants for their support in making this webinar a success. The recording of this webinar will be available on techgeek.com by Monday. Thank you all. Thank you, Raghavan. Have a nice day.
Yeah, thank you very much. All of you have a great weekend.
Thank you, Raghavan.